Today we're going to answer a very important question using the material from Chapter 9, which is natural convection. The important question we're going to answer is, well, the motivation for this is my former colleague, Hang Ban, was at some kind of party where there was hot dogs boiling in a pot. He stuck a fork in one, pulled it out, wanted to hand it to his child, and realized that it was too hot for the child to handle, and therefore posed the question: is it better to hold the hot dog horizontal or vertical to get it to cool faster? So we're going to answer that important question. So here are my I put a caliper to a hot dog, and that's a lie. I didn't. I made these numbers up. Hot dog diameter is ½ an inch, which is 0.0127 meters. I'm sure there's a hot dog like that out there somewhere. The length of a hot dog is 10 inches. Hot dogs are American, so I'm using American units, which we blame on the British. 0.254 meters. So I'm going to assume that the hot dog was was boiling, and at the moment it was taken out, and so we're going to set its temperature to 100 degrees C. So Ti is equal to 100 degrees C, and T infinity is 70 something Fahrenheit. We'll call it 20 degrees C, and which means that my film temperature, which you're all on top of right now, film temperature is the average of those two, and this time I'm going to do that average correctly. Half of 120 is 60 degrees C, and 333 degrees Kelvin. So the Nusselt number correlation for a horizontal cylinder from your text is this. I'm not going to quote an equation number because it might be different in the different versions of the text, and you can look it up. Of course, the driving parameter for natural convection is Rayleigh number, and we're going to have to compute what that is here in a second, but I'm going to write the correlation down first. Okay, there's our correlation. Involves a Prandtl number and a Rayleigh number. So we're going to need some properties, and we're going to need to compute our Rayleigh number. Rayleigh number, by definition, is acceleration due to gravity times beta times Ts minus T infinity times our length scale, which is diameter in this case, cubed over nu times alpha. So I'll make a little table here. At 333 Kelvin, alpha is equal to 27.4 times 10 to the negative 6 meters squared per second. Nu is 19.2 times 10 to the negative 6 meters squared per second. K is 28.7 times 10 to the negative third watts per meter Kelvin. That's K of air. Beta is 1 over T because air is an ideal gas at atmospheric conditions. And as always for a gas, I'm going to say my Prandtl number is 0.7. I'm waiting for some more codgerly professor of heat transfer than me to come along and say that I should really pay more attention to my Prandtl numbers. But given the lack of precision and a lot of the other things that we're doing here, I don't think it's ever worth chasing Prandtl number down to any more precision than 0.7. Okay, so putting in all these numbers for Rayleigh, I'm going to get 9.81 meters per second squared times 3 times 10 to the negative 3 Kelvin to the negative 1 times 80K is that temperature difference times 0.0127 meters cubed divided by nu and alpha, 27.4 times 10 to the negative 6, and 19.2 times 10 to the negative 6 meters squared per second. That equals 9.2 times 10 to the third. Now again, this is our horizontal case that we're working on here. And I should have asked you to, before I got going here, to speculate on which one is going to be the better case. One argument that you can make for the vertical case is that your Rayleigh number is going to be much bigger because the length scale of the vertical case is going to be the length of the hot dog, while the length scale for the horizontal case is the diameter of the hot dog. So that would have been my guess. I'm going to admit to that. And frankly, I haven't looked back at my solution. I wrote this down a year ago to see which is better. But I'm going to go with vertical for now. And you might get to enjoy me being wrong. Again, that's Rayleigh number, and it's good to put the length scale down as a subscript on that number. So if I take this, put this in Pratnall number into my Nusselt number correlation, I'm going to get that my Nusselt number average over the hot dog is 4.27, which is the average H times the diameter over the K. And that tells me that H is equal to 9.663 watts per meter squared Kelvin. Now I haven't computed a cooling rate here, but I am assuming that the cooling rate depends on H. And that's true if you go back to your cylinders, the transient of a cylinder, then that probably never asked us if it was vertical or horizontal. That's all comes in through the H parameter. So all I'm going to do is compute H, and that's my answer for the horizontal case. Okay, so now if I switch to a vertical case, and I'm going to run out of paper here, so I'm going to go ahead and go to the next page. If I switch to a horizontal case, I'm going to simply treat my hot dog like it's a unwrapped wall, a heated vertical wall at constant temperature. So in that case, my Nusselt number for that case, which is based on an L length scale, is 0.825 plus 0.387 Rayleigh based on length to the 1/6 over 1 plus 0.492 over Pratnall number 9/16 to the 8th 27ths, and the entire mess squared. That looks very similar to what we had before. I'm just going to show you what I had before to prove to you that indeed it's not exactly the same correlation. But it has a lot of the same powers in it, has a lot in common with it. So be careful. Don't get mixed up on which one you're using. All right, so now in this case, my Rayleigh number is G beta times Ts minus T infinity. Most of this remains the same, but what changes is this length scale. 0.254 meters to the cube power over nu alpha. Everything else remains the same except for this. And that gives me a much larger number. 7.3 times 10 to the 7th is my Rayleigh number now. So if I put that in, I get a Nusselt number that's much larger, which shouldn't surprise you, given this, and it's the Rayleigh number power. But remember that Nusselt number is a dimensionless heat transfer coefficient, and we use that same length scale here, although it's now just to the first power. This is going to tell me that H is equal to 6.28. So just to remind you, horizontal, H was, and these are both H bars by the way, H was 9.663. So that's a little surprising. I am wrong that for reasons that I really can't glean right now. According to this analysis, the horizontal is actually going to, or the horizontal case is actually going to have a higher heat transfer coefficient by about 30% and will cool the hot dog faster. So there's that's a pro tip for you in case you're out there and you need to cool the hot dog by natural convection quickly. According to this, you should hold it horizontally.